Hi class. Today I'm going to do a lecture for you, a complete lecture. This is lecture 26 on the integral and engineering momentum balance. The quick outline for the lecture is shown up here. Oh, I better switch to this guy. Hold on a second. Let me make sure I have my pen. Okay. So the reading today goes with Deen chapter 11, section 3. And there are three parts what we're going to cover. We'll talk about the integral momentum balance, then we'll talk about the engineering momentum balance, and I'll show some examples of problems like what are on your homework. So let's start with section 1, the integral momentum balance. So the last lecture we had before the exam, we talked about and derived an integral mass balance for an arbitrary region that I called a control volume. And remember that a control volume is just some fixed region of space. And I labeled some variables on this control volume. I said the volume of that control volume is called V, and it could be a function of time. The surface is called the control surface, and I give it a variable S. So V is the control volume, S is the control surface. It has a unit normal, that control surface, which is N. Here, the unit normal for the control surface, and that control surface can be moving with some velocity u. Along with that, there is the fluid velocity v that is interacting with the system. And with all of this together, I justified at least and wrote down an integral mass balance. So the integral mass balance looked like this. Let me scroll it up a little more. The integral mass balance was the time derivative of a volume integral of rho dv plus a surface integral of rho times the fluid velocity minus the surface velocity dotted with the unit normal ds equals 0. And I probably wrote this on the other side, there was a minus sign. Okay, so this is the accumulation term right here. And this term is the in minus out term when it's over here, but I think on this side this is out minus in. Okay, so these are the flux terms, the mass flux. And then this guy was the generation term. All right? So this was the mass balance. So it turns out that we can generalize this statement a little bit further, and we can write this as a general for any property. So we can generalize, this balance for any property. Okay, and I'm going to say that my general property is B. Okay, so what I mean by that is B is some property of interest. It could be, for instance, the mass, as an example. Okay, and I'm going to say that little b is the property per unit volume. So this would be, for example, the density. All right, and what I'm going to do is write down a general balance that looks a lot like this guy, but where I have rows, I'm going to put a little b, and where I have m's, I would put a big B. So what I do here is I'm going to write down time derivative of the integral of the volume, and then I'm going to have a little b dv plus a surface integral s of t little b times v minus u dot n ds equals, and now I need something else over here. I'm going to call this b generation. Okay, so what's going on here? So this guy right here, this is the convective flux, okay, of B across the boundary of my control surface. So if I have some general property B, that's what's getting convected out and in here. And then this is my generation term, generation of B. Okay, and this general property balance, when I write it in terms of anything and not just mass, has a name. Okay, and the book calls this something like a general integral property balance. Okay, and that name is kind of unique to the book. Most books call this something else. They call this the Reynolds transport. Oops, eraser came in there. Let me fix that. Transport theorem. Okay, so this guy here, when I write it in terms of any property, is called the Reynolds transport theorem. And what's kind of nice about this is that instead of having to go through this derivation again and again for different properties, I can write any property I care about and plug it in here. So today we're going to focus on momentum. Okay, and the momentum property B will then become mass times the velocity, and the little b will then be density times the velocity. Okay, so I just need to take those guys, plug them in up here to my Reynolds transport theorem, and I get the time derivative, the volume integral of rho v dv plus the surface integral of rho v times v that v was ugly. Let me fix that a little bit. V minus u dotted with n ds, and then that's going to equal well, I guess I'll still leave as b gen for a minute. Okay, which is going to be my momentum generation. Okay, and so we have these two terms already. So that's kind of nice out of the Reynolds transport theorem. And all we need left is to write down this term. So it turns out this is momentum generation and what are called diffusive fluxes. And it's not so important you know what that means. But I don't want to lie to you. I want to be accurate. So these are terms that generate momentum and diffusive fluxes. And what is that for momentum balance? Well, if you remember back when we derived the Navier-Stokes equation, the generation terms is equal to the sum of the forces for momentum balance. So I have the change in momentum over here, and this has to equal the sum of the forces. So this is like Newton's second law. Okay, so the sum of the forces in this case, I'm going to have a volume integral of body forces, dV, plus a surface integral of surface force or surface stresses times ds. Okay, so I have body forces and surface stresses, and those are going to be my total sum of forces. So we already know these guys. Hopefully this looks familiar. My body forces is rho g, that's gravitation, and my surface forces are going to be n dot sigma ds, where sigma is my total stress tensor. Okay, and I can expand that a little bit using what I know already about my total stress tensor, and this is going to give me an integral over s of minus np ds plus an integral over S of n dot tau, the viscous stresses, ds. Okay, so those are all the pieces. So if I write that all down, this is kind of a mouthful, right? Here's the final guy, the final equation for the integral balance. I need to take this piece and that piece and add on these three pieces. So let's see if I can get enough screen to write that down. I'm going to give myself a little extra space by going in the margin over here. d dt of the volume integral of rho v dv plus the surface integral of rho v minus u dot n ds is equal to this piece here, the volume integral of rho g dv minus the integral over the surface of n p ds plus surface integral of n dot tau ds. Okay, and that's the final guy. And I would put a, well, I'm going to try and put a box around it, but we'll see if it works out. I might give up. All right, so that's the integral momentum balance. And really this is just like a statement of Newton's second law, but it's for systems that are open. I can have velocities that move across the boundaries, and the control volume can move. It's more general than Newton's second law. Okay? All right, so that's section 1. All right, section 2. So just like the case with the mass balance, this general integral balance is not super useful, right? It's complicated. It's very general, right? It applies in all cases, but not very useful. So I'll write that. The integral balance always applies, but it isn't very useful. Okay? Instead, what we want to do is we want to pick a control volume that's smart, that allows us to make this a lot simpler. So we want to pick a smart control volume. Okay? And in this case, these are the following assumptions. We need to add a new piece up here, page after. Okay? We want to have a smart control volume, and a smart control volume has the following parts. Okay? It has discrete inlets and outlets. Okay? That was the same assumption we had in the mass case. All right? It also has a uniform density at the inlets and outlets. Okay? Inlets and outlets, again, is what I'm going to write I/O for inlets and outlets. But it has a couple more things that we need. All right? It needs a unidirectional flow at the inlets and outlets, at least on average. Okay? So a turbulent flow that's in the one direction, that's okay. All right? The second, or the fourth thing it needs is small viscous stresses at inlets and outlets. Okay, so what that means is that at these discrete inlets and outlets, I'm going to have my control volume go across a certain area. All right, and things that have small viscous stresses will be things like pipes, basically pipes. Okay, pipes in and out. Okay, that will have small viscous stresses. But there are things that don't have small viscous stresses, things like pumps or turbulent wakes. Okay, or turbines or fans. Okay, anything really complicated, sudden contractions or expansions. Okay, these are frowny face. These are not good. Pipes are a smiley face. Those are good. Okay, so we'll see cases with that. Probably not today, but we'll see more. All right, and then the last assumption that we'll need, assumption number 5, is a fixed control volume. Okay, so if I have these 5 cases, I am going to get a much simpler momentum balance. All right, these 5 will lead to the engineering momentum balance. All right, and I'm not going to derive this for you right now, but you can see my extra notes for how, if I use these assumptions, I can get to the engineering momentum balance. But I'll try not to bore you too much with the math. So I have my notes, or also it's on page 296 to 298 in Deen. Okay, there's also some information there on the derivation. So after this, okay, see that for the math, all right? All right, I just write that there. For the math, okay, we get this guy. So d dt of mv, okay, of the control volume. So the change in momentum of the control volume is going to equal the sum of all the inlets of wi, ai, vi, where w, this is the mass flow rate, okay, and this ai I'll explain in a second, minus the sum of the outlets, wi, ai, vi, okay, and this is the velocity, okay, in both of those cases, plus the sum of the forces, okay, where this is going to have pressure, mg, etc. Okay, so what is this AI? I need to write down what that is. So AI is equal to the average of the velocities squared divided by the average velocity squared. Okay, so the difference here is the squared is inside. So this is like a variance of the velocity divided by the velocity. So what I'm doing here is, say I have a pipe. I want to average the velocity profile. If I take that v dot v, that's going to give me v squared. If I take that average, okay, over that area there, that gives me the top. And if I just take the average of v, okay, dotted with the average of v, that gives me average of v squared, okay? And that ratio is AI, okay? And this has values that you could go calculate. Maybe that would be a good homework problem, but I don't think I gave it to you on this one this year. So if it's plug flow, well, let me write it the way we would normally do in math. It's 1 if it's plug flow. Okay, remember that plug flow is a velocity profile that's just straight. Okay, so if it's exactly straight plug flow, it's 1. it's almost 1 if it's turbulent. Remember that turbulent flow is very flat and almost like plug flow. So this is 50 over 49. That's 49. Oh, I made it worse. 49. I don't know if that helps any, but 50 over 49 for turbulent. And laminar flow is not as close to 1. Laminar flow. Okay? So turbulent flow, we often make that one 1 because that's so close to 1. And plug flow is 1. Laminar flow is different enough that we'll plug that in. Okay? So this is that A right there. Right? Same thing with this W, A, V. And this, of course, is the mass of the control volume and the velocity of the control volume. Okay? So that's the engineering momentum balance. So if we pick a system with these properties up here, these assumptions, we get this engineering momentum balance. So let's see if I can put this in a box. I'm going to have to skip some of this stuff because I drew all these arrows around it. But there we go. Okay, so that's our engineering momentum balance. All right, so I've talked a lot, but let's get to a couple examples. So 3 is examples. Boom. All right, so example A, I'm going to do a flow in a nozzle, which control volume 1 is what I'm going to call it. Okay, so flow in a nozzle. So let's draw, I'm going to add a new page here. So I want us to consider flow in this geometry, flow in a hose. Hose has an S. In a hose with a nozzle. So here's my hose, okay, and at some point it narrows down, okay, to a small point. So I have some flow in here, and then it comes shooting out here faster, okay, through my nozzle. Maybe I'll just drop that last arrow, okay? And suppose I know out here what the pressure in is, and I know what the velocity in is, and I know I'm going to say it's just in this direction, the X direction, so I'm just going to say V in, and I know the area at the inlet. And out here, right at the tip of the nozzle, I know the outlet pressure, which should be equal to the atmospheric pressure. I know the outlet velocity, and I know A out. I know the outlet area. Okay? So, suppose I'm looking at this case. Let's ask the question as follows. Let's ask, what is the force of the nozzle needed to keep the hose from moving? Okay, so if I put some force, say I have to grab onto this, or if I have to fix it, with some bolts or something, what is the force that I would need to keep that hose from moving? Okay, so step 1 is to draw a control volume. Okay, so maybe take a second and you try and draw a control volume. Pause the video, see if you can draw one. Okay, hopefully you paused the video. If you didn't, maybe you're just trying to be time efficient, but it probably helped you learn. Okay, so I'm going to draw a control volume. I'm going to draw a control volume that looks like this, that goes on the outside of my nozzle, just outside of it, and crosses in front right there. And that's as close as I can get. Sorry, I kind of messed up there, right? And let me just check my assumptions, okay? Discrete inputs and outputs, check. Yep, it has that. So I have uniform density at the inlets and outlets. Yes, it does. What about unidirectional flow at the inlets and outlets? Well, I didn't say anything about that, so let's come up here and let's assume turbulent flow. That's a pretty good assumption for a nozzle where water's moving fast. So I'm going to say yes, unidirectional flow, at least on average, that's true. Small viscous stress at the inlet and outlet. And I said for pipes that was good. So yep, I'm good there. Okay. The last one is fixed control volume. And mine's fixed, it's not moving, so that's good. Okay, so I can use the engineering balance. So that'll be 2, will be right my balance. Okay, so for my balance, I'm going to draw a little diagram. I'm going to redraw my control volume. And I'm going to do something that's kind of like a body force diagram, but also has these input and output streams. So I'm going to say, well, I have some input and output streams. I've got W in, A in, V in. So this is my momentum convected into my box. And on the other side, I'm going to have W out, little a out, V out. Remember, this A is this ratio. So A in is A out. That comes from turbulent flow, which is 50/49. I'm going to say that's about 1. Okay, so I'm just going to kind of neglect those guys. That's 1. Okay, so I'm going to have W in, W out, V out. All right, and then I have, so that will take care of some of these pieces in my balance, right? That's that one and that one. And I need to write down now my forces. So let me write this as if it's a body force diagram. And I'm going to say I have on this side, I have the pressure in times the area in. Okay, because up here on my nozzle, I've got the pressure in all along that side. So that's P in up along there. Okay, over here, I'm going to have pushing the other way, P out, A out. All right. Oh, excuse me, not A out. I'm wrong there. Not A out. It's going to be P out, A in. That's important because look how I drew my control volume. I said that was A in. I drew a box, so that's also A out. And well, why is it P out, A out? Well, P out is the same as P atmosphere, A out. I said that when I have the velocity or the fluid coming out, it has to be at atmospheric pressure at the outlet. So I also have atmospheric pressure pushing on this part and pushing on this part, and it's also pushing on that part. So I have atmospheric pressure all along those guys. Okay, so I have P out times, oh man, I totally screwed that up, times A in. All right, because that area along that whole part, that's A in as well. Okay, A out is only that little piece right there. So P out, A in. And then I need one more term. I need to add the force of my nozzle. And I'm going to guess that my nozzle is going to push back in that direction. Okay. It doesn't matter if I put it on the other side though, because my derivation is going to tell me whether it's positive or negative at the end. But I'm going to guess that my nozzle has to hold it back rather than hold it for push it forward, okay, based on physical intuition. Okay, all right, 3. Now I'm going to do, I need to write my balance down before I get to 3. So I'm going to say the sum of the forces is 0. That's what that the accumulation term, so the change in momentum of my box is 0. So that term I'm going to say 0. And why am I going to assume that? because that's the question I asked. What is the force needed to keep the hose from moving? So I'm going to say that's equal to 0. And then I'm going to set it equal to these terms. So I have W in V in minus W out V out, because I have that convecting in, that convecting out. Okay, and then I have my force terms. So I'm going to have plus, because this is in the positive direction, P in A in, minus, this is in the minus direction, P atmosphere A in, minus F nozzle. Okay, there we go. So that's my balance. Step 3, guess I'm putting parentheses around it. Step 3 now is to just do math and to solve the problem. Okay, so why don't you take a second and rearrange this and see if you can get this down in terms of, and simplify this equation. Okay, hopefully you did a little bit of the algebra so you're awake, but let me show you my algebra. So I'm going to rearrange. I'm going to put F nozzle on the left hand side, and this will be W in V in minus W out V out, plus I'm going to move A in out. I'm going to have A in multiplied by P in minus P atmosphere. Okay, and now I'm going to make a substitution here. So I know that W in has to equal W out from a mass balance, right? So I have flow rate, or the mass flow in has to equal the mass flow out. And I can say that that's equal to rho A in V in. But I can also say that's equal to rho A out V out. And I can use that to find a relationship for V out, right? So I can say that V out is equal to V in multiplied by A in divided by A out. And I do that by canceling the rows, all right, and dividing by A out over here. So I can now make these substitutions in here. So I'm going to take rho A and V in, put it in for W in, and rho A and V in and put it in for W out, and get rid of W out. And that will make my expression a little bit simpler. So let me get a new page here to do that. So substituting that all in, I get rho A in V in minus, V in, and then I have another V in, so that'll be a V in squared, minus W out is rho A in V in, and then V out is equal to V in, so I have a squared there, multiplied by A in divided by A out. Then I need to add that other piece in, plus A in. I'm going to rewrite this P in minus P atmosphere as P in gauge. Okay, so I'm almost done. So F nozzle is equal to, and let me factor in an A in because there's one in all of these pieces. So I'm going to have A in multiplied by rho V in squared, which I can pull a factor out there too, and I get 1 minus A in divided by A out, plus P in gauge. And voila, that's the end answer that I get. Ugh, terrible. Let's see if I can complete the rectangle. All right, there we go. So what does this mean? Just to sort of summarize, I'm asking, I have this nozzle here, okay, and water's coming in and water's squirting back out, and I say, how much force do I need if I bolt something on and it goes back in that direction? All right, well, I have a pressure in, so I'm going from a pressure here out to atmospheric pressure out here. So because there's a pressure pushing, all right, so this is the force for the pressure, okay, that I need to counteract the pressure. And then this guy, this has to do with my inertia, right? So if A in equals A out, if those are the same, then that's 1, and that 1 minus 1 goes to 0, and I have no inertia change. But on the other hand, usually A out is less than A in. So this guy will be bigger than 1, and this is negative. All right? And this is kind of like what happens when you have a bottle rocket and you have something shooting out and it pushes back that way. So this is negative. So that term will actually decrease the force I need. So if I make my A out small enough, I can maybe make them exactly the same to cancel out. But it could be that my nozzle actually ends up pushing. I need to bolt it and push it that direction if it's speeding up enough to go out there. Right? So that's physically what's happening there with my nozzle. Okay? So let's see. I'm not sure what my time is here. So if I'm running out of time and you're playing this in a lecture or something, you can go ahead and stop. But I'm going to keep going on example B just in case you want to see one more. Okay? So this will be flow in a nozzle, okay, with a control volume 2. And I wanted to do this example because I wanted to show you how the control volume affects the end answer, okay, and or how it affects your analysis as you get to the end answer. Okay, so the other control volume is not the only control volume you can pick to solve this problem. So I'm going to do, a new control volume that gives the same answer. Okay, but it's a little bit subtle, so I wanted to kind of talk about this one. So the first step would be to draw a control volume. Now, maybe some of you, when you thought about this, you drew your nozzle, okay, and you drew a control volume that looked like this. Inside, so assume like that one, I hope would be a little closer. Let's see if we can get a little closer. Okay, so I drew it just inside of this guy. All right, so I'll maybe make that point inside the nozzle. All right, and if we go through and check our assumptions, discrete I/O, okay, that works. All of my assumptions, they all work. Okay, check, check, check. This all works. So this is completely valid. All right, so for that case, so let me come down to 2. And let me say now we write my balance. Okay, so now I have this guy that's not shaped like a rectangle. It's shaped, I guess I don't know exactly what that shape is. Almost like a pentagon, but with a little end cut off. All right, and I still have here Wn Vn, where I'm going to again assume that An is approximately the same as A out, which is about 1. I guess I'll assume those are equal, and then that's approximately 1. All right, so I have Wn Vn, and I have W out V out coming out the nozzle tip. And I still have P in A in here, but on this side I have P out A out. And now it's because I have a balance only on this piece right here, P out A out. Okay, I don't have pressure coming out this part here because that's not where I drew my control volume. All right, this is inside the walls. Okay, and any pressure that's pushing there is pushing on those walls, not out this part. That's different than this case up here because I drew my control volume up here outside. So this piece outside, there is atmospheric pressure pushing all along that part. Okay, so different control volume gives me a different pressure, but then I can do F nozzle right here. Same thing. Okay, so I can write down the balance. Now that I did my little diagram, 0 is equal to W in V in minus W out V out, because in coming out, and then I have my forces plus P in A in minus P out A out, okay, minus F nozzle. Okay, last part here will be math. Okay, I can go through the same analysis that I did before. I'm going to add a new page again. Okay, and I'm going to skip some steps, okay, because I don't want to take too much time doing the algebra. But if you plug in the same stuff we did before, what you come down to is the following. So I'll leave some dots here, okay? Do on your own. Okay? I get that the nozzle is A in times by P in minus P out. But now this has an A out divided by A in it, okay? Plus this other term, rho V in squared, multiplied by 1 minus A in divided by A out. Okay, so now, wait a minute. This is different, right? Above, instead of P in minus P out with this junk, right, I got P in gauge. This part is the same, but this was P in gauge. What's going on here? Okay, now what's going on here is that I drew my control volume inside the nozzle. So this is only telling me about what the force of the fluid is on the nozzle. It's not telling me about the net force that includes the atmospheric pressure on the outside. Okay, so if I want the net force, to include the atmospheric pressure, I need to have that be, let's make it minus because it's going to go in the negative direction. I need to have that be the F of the nozzle, okay, plus atmospheric pressure multiplied by the stuff on the outside of the control volume that I didn't take into account, okay, on this part out here that wasn't this internal piece. Well, what is that part? That part is A in minus A out, right? Because this A in, that's the one side, and A out, that's that little side. So A in minus A out is all of that stuff, okay? That's the same area as, maybe I'll draw it differently. That's that piece to there, okay? And that piece to there, okay? So that's A in minus A out. So if I'm looking at a circular nozzle, okay, I take out that part and it's that outer part. All right. So now if I want to look at the F on the nozzle net, okay, that's the F nozzle net, okay, I'm going to get F nozzle minus P atmosphere times A in minus A out. Okay, and I can take F nozzle right there, and I can put that piece in there. All right, and a little bit of algebra will show. Notice that this is P in A in, so I can. It's kind of useful to pull that back out. So if I have P in A in minus, and this multiply there gives the A outs cancel, minus P out A out. Okay, plus, and then this will be rho V in squared A in times 1 minus A in over A out. Okay, so this is F nozzle rewritten. And now I'm going to subtract P atmosphere A in plus P atmosphere A out. And look, P out and P atmosphere I said were the same, so that guy cancels there. Okay, because remember P out equals P atmosphere. Okay, and now I have P in minus P atmosphere. That's going to give me P in gauge times A in. And so I end up with the exact same expression that I had before, which is A in multiplied by P in gauge plus rho V in squared, factor that one out, 1 minus A in divided by A out, close brace. Okay, so the moral of the story, okay, now this is the same as A. Same as A. So the moral of the story is be careful about your control volume and what it means. All right, so if I do a balance, momentum balance on the inside of the nozzle, I'm only going to get the forces on the inside of the nozzle. But if I do a control volume on the outside of the nozzle, I'm also going to get the forces from the atmosphere and other parts on the outside of the nozzle. So you need to be careful about what the question is asking in order to make sure that you know whether it's asking, say, for the net force or the other force, and make sure that you draw your control volume appropriately. All right, I think that is all I have for you. With that, I wish you the best and have a good one.